We know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. To see the sunrise tomorrow, inspire the world to follow. Our life truly has some unseen.
Okay, so in the curriculum of electrical machine 1, we are going to discuss module number 5 on 3-phase induction motor. And a very good morning to all of you. I am Sumanto Kundu, Assistant Professor of Department of Electrical Engineering, is going to discuss the topic on vector grouping of 3-phase transformer. Now, the objective and outcome of this lecture is to become familiar with the vector grouping of transformer. Okay, so let's start lecture number 2 on vector group of transformer. So, introduction to vector grouping. This vector grouping of transformer is also known as clock method or angle designation. Okay. Now we know the transformer can be of different topology, means transformer has different connection diagram such as YY, Y delta, this is also known as star delta, delta delta, and delta Y, which is also known as delta star. So these are the various transformer connection. Now in the above various transformer connection, the high voltage and low voltage may or may not have a phase difference between them. If it is a start transformer, if it is a start transformer, if it is a star transformer, so there is no phase difference. But if it is a star delta transformer or delta star transformer, so in between this high voltage and low voltage there exists a phase difference. Okay, there exists a phase difference. Okay, now in the vector group we indicates this phase difference which exists between that particular transformer connection. Now the question that must spring up into your mind, that apart from this reason, what are the another reason for the development of the concept of vector grouping? Now we have learned from our first class that there are two types of 3-phase transformer. One, 3-phase bank of transformer, or a single unit 3-phase transformer, a single unit 3-phase transformer. Now in this 3-phase bank transformer, we connect 3 individual single phase transformer in parallel. Now transformer from one group cannot be parallel with the another transformer, because in that case it will violate the condition of parallel operation of the transformer, that is the voltage ratio same, phase difference should be the same. So determination of vector group is very essential to connecting two or more transformer in parallel. Otherwise, if we doesn't do this, there will be a large circulating current because of relative phase difference between secondary line voltage being connected together. So that means that means that means so we know three single phase transformer. So this is one transformer, this is low voltage or secondary of the transformer, this is transformer 1, and in this fashion this is transformer 2. So now this low voltage side of transformer 1 and this low voltage side of transformer 1 are connected in parallel. Similarly, the high voltage side of this and high voltage side of this transformer are also connected in parallel. Now, if these two transformer don't have the same phase difference, don't have the same phase difference, then what will happen? There will be a flow of circulating current. There will be a flow of circulating current due to this existence of phase difference between this line voltage of this transformer secondary with the line voltage of transformer 2 secondary. Okay, and this circulating current is not desirable because circulating current reduce the kVA output, kVA capacity of the transformer. Okay, now look into this picture. So in this picture, this is the primary which is star connected, this is secondary which is also star connected. So this is transformer 1, this is basically a YY transformer or star transformer, and this is a star delta transformer which is my transformer 2. Okay, so this is a star star and this is a star delta. Now look, this secondary are connected with this load terminal of ABC. So C with C, A with A, B with B. Similar for delta also. Now look, for this transformer, what is the line voltage? The line voltage is this A1, B1, this A1, C1, and this B1, C1. So these are the line voltages of transformer 1. Now for this transformer also it is same. A1, B1 line to line voltage, B1, C1 line to line voltage, and C1, A1 is line to line voltage. Now look, this is the star connected line to line voltage A1, B1, and this is my A1, B1. So if we put here, so this is my A1, B1 for delta, and this is A1, B1 for star. So you see there is exist a 30-degree phase difference, and this phase difference is responsible for the flow of circulating current. Okay, so that is what we have discussed. So this result in a flow of circulating current in the phases even when the transformer are no load. So there is no load in the secondary. but still there is a flow of current, so which is not desirable, which is detrimental. So this is not acceptable in case of parallel operation, and that is why vector grouping, clock method, angle designation is so important to study. Okay. Now nomenclature. So this is the nomenclature for two winding transformer. Okay. Now according to IEC, that is International Electrotechnical Commission, has the standard code for determination of the vector group. What is that? Now high voltage winding connection is represented by a capital letter like Y, D and Z. Y for star, D for delta and Z for zigzag, or this is also known as interconnected transformer. Okay. And low voltage winding represent by a lowercase letter, which is my second symbol, by YDZ, similar to star delta and zigzag connection. And the third symbol is the phase displacement between the high voltage and low voltage line induced EMF. So this is the phase difference between high voltage and low voltage, line to line or line to neutral. We can take line to line voltage or we can take line to neutral, that is phase voltage. So that is defined as a clock hour number. We will define the clock method. Okay. Now suppose it is a YD transformer. So first, that means it is a polyphase transformer. Second, you look, the capital letter first symbol is, I have discussed, HV winding. So HV winding connected in star. Similar way, secondary is connected in delta. And third, it is designated by in a clock. This is 12, this is 11, 1, 3, 6, 9. So it is defined this 11 position. So this is basically a 30-degree leading position of the from the 0 hour position, and this 12 o'clock position is the 0 hour position, and this total angle is 360 degrees. So each of them is the difference between two consecutive digit of a clock is 30 degree, because 360 by 12 is nothing but 30. We will discuss this later also. So this is the nomenclature. Okay. So this is the nomenclature for two winding transformer. But if a tertiary winding is present, then our nomenclature will be a bit different. So there will be a first, second, third and fourth symbol will be there, but this is not in the scope of our syllabus, so we are not going to discuss this in details. But if anyone has any queries, you can contact. I have given my email ID at the end of my lecture. Okay. Now, so this is the clock position. So this minute hand is the represented the high voltage EMF, which is the larger arm. This is the hour hand, which is my shorter arm, that is represented the LV side induced EMF. And the anti-clockwise rotation is taken as positive or leading, and negative clockwise rotation is taken as negative angle or lagging. That's why we have told in our previous example in case of YD11 that it is 30 degree lagging or ahead with this 12 o'clock position, and this 12 o'clock position is known as 0 position. This 12 o'clock position is known as 0 position. Okay, so this is the most simplest way I am trying to make clear the vector grouping to you people. This is the most easiest way I am explaining. Okay, so this all I have discussed so far, that HV voltage phasor is considered as minute hand, a longer arm of a clock, and always it is always set to 12 o'clock position. So this position of 12 o'clock position of the minute hand is fixed. Only the hour hand position, that is the low voltage phasor, it's rotate according to the phase position with respect to the HV winding. So this is a fixed position, and longer arm is the free to move position. So our hand can take 12 discrete position. Accordingly, we designated it 1, 2, 3 up to 11. Accordingly, we can designate it YD11, YD1, DD0, YY6, and so on. And I have already mentioned that the angle between any two consecutive number in a clock is 30 degree, because 360 by 12 is 30. This is also I have discussed. So angle between hour and minute hand can only be multiple of 30. So suppose in 11 o'clock it is 30 degree. Now if it is in 10 o'clock position, so it is 60 degree, multiple of 30. So accordingly it gives the information of relative phase difference between high voltage, which I have mentioned, and low voltage as per time indicated on the clock. If it is in 11 o'clock position, it's 30 degree phase difference leading. If it is 1 o'clock, then 30 degree lagging. If it is 6 o'clock, minus 180 degree lagging, 180 degree lagging, and so on. Okay. So this is also I have mentioned, anti-clockwise direction is taken as positive already, and clockwise rotation is taken as negative or lagging. Okay. Now, so these are the different nomenclature of clock method. So this is group number 4, this is group number 3, this is group number 1, and this is group number 2. So if you in group number 1, both the minute hand and hour hand coincide with each other. That means high voltage line phasor and low voltage line phasor coincide with each other. So there is no angle between them. So it is a zero phase displacement position, zero phase displacement position. Similarly, 11 o'clock minus plus 30, 1 o'clock minus 30, and 6 o'clock is 180 degree phase shift, lagging phase shift position. So there are basically 4 groups. Apart from this, the other clock position is also there, but these are the traditional normal 4 groups which we are going to discuss. Okay, so let me okay. So up to this we have discussed. So now look, this is a 3-phase single unit transformer. Now look, this is A phase, this is V phase, this is C phase. because we are discussing with the three-phase transformer. Now, for A phase, this is my high voltage side, this is my low voltage side, and both this high voltage side and low voltage side winding belongs to the same phase because they are owned on the same limb of the core. So this is my limb and this is my core of the transformer. And look, for a particular phase, both the high voltage and low voltage are interlinked with the same limbs. Similar is true for V phase, similar is true for C phase. It is denoted by HVA, this is LVA, and so on, HVB, LVB, HVC, LVC. And the two terminals of this high voltage side A1, A2, correspondingly small a1, a2 for low voltage side, and so on for A and B phases. Okay, now look this dot convention. So what is the meaning of this dot convention? The meaning of this dot convention is that, just hold on. So what is the meaning of this dot convention? Now, if this is my high voltage side and this is my low voltage side, and suppose this is A2, this is A1, this is A2, this is A1, and this is dot, this is dot. What that does it mean? Now its mean is that when A2 is positive with respect to A1, this secondary side or low voltage side A2 is also positive than A1. So means A2 A1 is positive. If then A2 A1 is also positive. Means if this is the voltage waveform of the high voltage side, this is the waveform of the low voltage side. Look, there is no phase difference exists between them. Now if this dot instead of here, if it is remain here, so that means if A2 is, when A2 is positive with respect to A1, in secondary it is opposite, A1 is positive with respect to A2. That means if A2 A1 is positive, that means A1 A2 is negative. So in that case, the primary side, if this is the waveform of the primary side, what should be my waveform of secondary side? This is the waveform of secondary side. Look, there is 180-degree phase difference exists between this high voltage and low voltage side. Okay, every instant I have draw a little bit different way because I am not a very good artist. So basically all the time instant will be same for both this high voltage and low voltage side. So this peak will occur at same, this zero will occur at same position, again this peak will occur same position, and so on. So this is exist a 180-degree phase difference. So that is the meaning of dot convention. Okay, so that what I have discussed. Now before we draw the connection diagram or phasor diagram of vector grouping, these are the few standard procedures which we will maintain. The first one is, I have already mentioned, you know from your knowledge of basic electrical or electrical machine, the phasor is always rotate in anti-clockwise direction, and the phasor of HV and LV winding for a particular phase remain parallel to each other. Now why? Now just few minutes back we have seen that the high voltage winding and the low voltage winding both are connected to the same limb of the core, owned to the same limb of the core. So if it is connected to the same limb of the core, so this high voltage and low voltage winding of the same phase. Suppose we are discussing with A phase, we are not discussing with B or C phase, but the analysis is same for true for both these B and C phases. So now, since if HV and LV winding of same phase are put on the same limb and they are linked by the same mutual flux, so as because they are in the same limb, the flux linking this winding and this winding is same. It is not different. So if it is same, the EMF induced is also same and in same phase, that is the zero phase displacement. And as we have seen that if we have mentioned or we have to depict in pictorial way to the zero phase displacement, so it is basically, if this is the phase of high voltage side, so this is the phase of low voltage side, both will coincide. So basically both are parallel to each other. That's why we have mentioned the phasor of high voltage and low voltage for a particular phase remain parallel to each other. The position of A2, B2, C2 of high voltage terminal, we have seen that A2, B2, C2, A2, B2, C2, A1, B1, C1 are the HV terminal, and the similar is true for low voltage also. So this position of A2, B2, C2 is always fixed, and remain in top, bottom, in the remaining top, bottom right and bottom left corner of a equilateral triangle. So this is basically fixed. This position will not change. So this is A2, right A B2, and in the left it is C2. So this position is whether it is a, so this is my delta's equivalent star. So this is my delta equivalent star. So it is, this position of the primary is fixed, and keeping this in mind that this position is fixed, phasor of star delta connection of HV side must be drawn in different position. So we have to keep these things in mind. Okay. And the phase sequence of HV and LV side remains unaltered. If HV side is ABC, then LV side is also ABC. It's not will be ACB. Now, just few minutes back we have discussed about dot convention. So suppose this is A2 and this is A1. Okay, this is A2, this is A1, and suppose this is my dot convention. So that means A2 is positive. When A2 is positive, then A1 in secondary side, A2 is positive with A1. Okay, that is what I have discussed. So this is basically start of the winding and this is the finish. That means A2, A1 is positive. That means start to finish is positive. So if start to finish is positive, then finish to start is negative. That means A1, A2 is negative. A1, A2 is negative. Are you getting my point? If A2, A1 is positive, then A1, A2 is negative, because start to finish is positive. This is start, this is finish. So finish to start is negative. So this is the basics to draw a different vector group. And this is the first group, that is zero phase displacement, zero phase difference, and under this category there is YY0, DD0, DZ0. But we are not going to discuss zigzag connection or interconnected transformer because this is not in our scope. So let me discuss these two connection, YY0 and DD0. Okay. first we will draw the winding connection, then phasor diagram of induced voltage and vector groups symbol. Okay, that is the clock designation. Okay, so let me first draw the YY connection, although here it is shown, so let me draw a bit for better understanding of you people. So let me draw first high voltage 3 winding first. So this is my this is my 3 winding of high voltage side. Similar, there will be 3 winding for low voltage side. Okay. So this is, and this is I am drawing the winding diagram, winding connection diagram. This is my winding connection diagram. Okay. So now give me the terminal name accordingly. Okay. So this is my A1, A2, B1, B2, C1, C2. Similarly, this is my A1, A2, B1, B2, small c1, c2. Okay. Now we are drawing the star-star connection YY0. So we know in star connection, there is a neutral point. So this is A2, this is my B2, this is my C2. I told that it will remain fixed for primary side in the equilateral triangle, top, bottom right, bottom left. So obviously this is A1, this is C1, this is B1, which is forming the neutral point. Okay. So what I will do, I will form the neutral point by shorting that A1, B1, C1. So this is forming my neutral point. And this is dot. So this is start to finish. So A2, when A2 is positive with respect to A1, so A2 is positive with respect to A1. So if A2, A1 positive, then A2, A1 is also positive. Okay. So this is also positive. This is also positive. So similarly, what we will do the similar thing for secondary. So we will short A1, B1, B1, C1, and that will form my neutral point for the secondary side. Okay. So this is my star-star winding connection. Okay. So for this connection, we are first drawing the winding connection diagram first. But in most of the cases, we will draw first the secondary phasor diagram, then primary phasor diagram, then the secondary phasor diagram, and then we will draw the winding connection diagram. We will see in later cases. Okay. So this is the winding connection diagram. Now let me draw the phasor first. So this is my voltage phasor diagram. So in voltage phasor diagram, what now we told that this is a star connection. This is a star connection. This is the high voltage side, and this is the low voltage side. Okay. And this is connected to load, and this is always fixed position. I told previously A2, B2, C2 position is always fixed. So this is A1, B1, C1, which form the neutral point, and this is connected to a AC voltage source. This is connected to a three-phase variac, three-phase auto transformer or variac, which is providing the AC supply. Now, what is the phasor diagram? So this is my V, this is my V A to N. We are considering the line to neutral voltage, so this is my VAN. This is my VBN, capital V, sorry, and this is my VCN. So there is no phase difference. So secondary phasor is also will be parallel to the same. So if we draw the secondary phasor, so in parallel with VAN, we will draw small VAN parallel to V, capital VBN, small VBN, and CN. So look, VAN in parallel, this is parallel to this, and this parallel to this, and we have considered here line to neutral voltage. If we consider the line to line voltage, look, it is also the same. This is line to line voltage VAC, this is VAB, and this is VBC. This is also VBC, VAB or VBA, and this is VAC. Okay. So look, this is also parallel to this. This is also parallel to this, and this phasor is also parallel to this. So there is no phase difference. So 0 degree phase difference. So 0 phase displacement. That is the group 1. Okay. So now if we draw the phasor diagram, easily we can draw the connection diagram. Look, A2, B2, C2 are the terminal, and A1, B1 is shorted for primary side, and similar is true for secondary also. A2, B2, C2 are the load terminal, and rest of the terminal are shorted. So A1, B1, C1 is shorted, neutral point. This is my terminal, primary terminal or HV terminal, and this is shorted. This is my load secondary terminal. So this is the winding connection diagram. This is my this and this figure 2, and this is figure 3, and this is my figure 1. So winding connection diagram, voltage phasor diagram. And if we want to draw the clock diagram, so clock diagram will be so let me draw the clock first. So this is a 12 o'clock position. It's the minute hand, that is the larger hand. It will always fix to this position. Okay, this is my 3, 9, 6 o'clock position, and it is 0 phase shift. So the hour hand will coincide with this high voltage phasor, because this is the minute hand, which is my high voltage phasor. So this is my hour hand, which is my low voltage phasor, and our minute hand is my high voltage phasor. So both are coincide. So that means 0 degree phase difference. So this is clock diagram, this is voltage phasor diagram, and the upper one is winding connection diagram. So similar way, suppose we want to draw D0 0. So first winding connection diagram, let me draw the 3 winding first quickly. So this is also for low voltage side. So now I have drawn the low voltage side. Okay. So now what I will do? I will draw the phasor diagram first. Okay. So let me draw the phasor diagram first. So let me draw the voltage phasor diagram. Voltage phasor diagram. Let me draw this first. Let me draw this first. Okay. So I have told that A2, B2, C2 position is fixed for a equilateral triangle. That is fixed. So delta delta. So this is my delta delta transformer. Equilateral triangle. So this is A2, this is B2, this is B2, and this is my C2, and this is my equivalent star of the delta. So this is A1, B1, C1 is basically forming the virtual neutral position for delta. Virtual neutral. Okay. So look, if this is A2, this is B2, so another terminal will be A1. So this is B2, another terminal will be B1. This is C2, another terminal will be C1. Here also you can take A1. Here you can also take, by not taking A1 here, you can take A1. So both are same. So now see, A2 C1 is connected. So A2 C1 connected, B1 C2 is connected, and A1 C2 is connected. Okay. So it is a zero phase shift group 1 position. So secondary will also be the same. So secondary, there will be no phase difference. So let me draw the first, the equivalent star for secondary. Okay. So this is my line voltage for delta, that is my A2 B1, A2 C2, and B1 or this B1 C1 or A2 C2, both are same. Similarly, line voltage for this is A1 C2, A1, let me draw A1 B1 and B2 C2, and here it is A2 B2 and B2 C1. So these are my line voltages, and these two are same. These two are same. These two are same. So zero phase difference. So here also will be the parallel same, because then only zero phase shift difference is possible. So I have not able to draw this is perfect equilateral triangle, but this should be a perfect equilateral triangle. So similarly, this will be my A2, this will be my small b2, this is C2, this is my A1, this is my B1, this is my C1. So look here also. So this is B2, this is B1, this is C2, so this is C1. So look, it is also true for, so for this is for high voltage side, connection. So for low voltage side, it is similar. Look, A to C1, A to C1, B1 C2, also B1 C2, B2 A1, B2 A1. Here also A2 C1, B1 C2, and sorry, here it will be A1 B2. So look, same for zero phase displacement. So now we have completed the voltage phasor diagram. Now let me draw the connection diagram. So for connection diagram, so this is A2, this is A2, B2, C2. So this is my A1, B1, C1. Similarly, this is my A2, B2, C2. So this is my A1, B1 and C1. Okay. So now the connection is A to C1. So let me connect A to C1. Then B1 C2. Then B1 C2. So sorry. It will be A to C1. A2 is connected with, or we can say A1 is connected with B1 B2. A1 is connected with B2. So let me connect. Let me connect A1 with B2 first. So A1 is connected with B2. So A1 is connected with B2. Now B1 is connected with C2. So let me connect B1 with C2. And the other is A2 connected with C1. So let me connect A2 with C1. Okay. So now this is forming the delta connection, and terminal will be bring out, as we know, this is A2 terminal, this is my B2 terminal, and this is my C2 terminal. Okay. So similar is true for secondary. Okay. So secondary, let me check. A2 C1. So A2 is connected to C1. Then B1 C2. Then B1 is connected to C2. And B2 A1. So A1 is connected to B2. and the terminal load terminal will bring out from A to B2 and C2, because A1, B1, C1 and here A capital A1, B1, C1 forming the virtual neutral. So from here the terminal will not, we cannot able to bring out the terminal. So these are the terminal of load side and these are the terminal of the input or supply side. Okay. So this is my connection diagram. Now let me give the dot notation. So this is, here is dot, here is dot, here is dot. That means A1, A2 is positive. So here is also it will be true. So A1, A2 is positive. That means start to finish. Start to finish positive. So this is all about the group 1 connection. In our next class, we will discuss the other vector group connection. Okay. So thank you. So let me check quickly first. So look, say what I have done. Same for pi by 0. It is very simple. And for look, A1, B2, B1, C2, A2, C1 sorted. Similar for secondary. And this is forming the ED0. And this point, which is forming the virtual neutral, that A1, B1, C1 in primary, and here is the A1 small A1, B1. So terminal must be brought out from A2, B2, C2, and load terminal should be small A2, B2, C2. And this is, we are not going to discuss because this is not in our scope of discussion in our syllabus. Okay, so this is all about today's class. Thank you very much. So these are the reference book. Also, you can read the book of MG Say book, MG Say book, SSN book. These are the very good books. Okay.